Thank you very much for the introduction, and we are going to present the most relevant results of the presentation entitled An Environmental Solution to Polystyrene Wastes by means of terpenoids and carbon dioxide that have been developed in the Institute of Chemical and Environmental Technology. The global plastic production is increasing yearly by 9 million of tons, reaching around 280 million of tons in the last year. And as we can observe in the graph, it's following the global patterns that the plastic industry started in the 1950s, following an increase of 9 or 10% per year. Among the most important, or the relative size of the plastic industry, has been mainly applied in the packaging, building and construction, automotive, electrical and electronic application. Among the big 6 kind of plastic, the polystyrene is produced around 2 million of tons, and due to its versatility and its important demand, thousands of tons of this plastic are being disposed of into environmental municipal solid waste. The main step of the plastic life cycle is shown in the slide, from converter to disposal or recovery. In the last year, around 47 million of tons were converted from the demand in Europe, and around 25 of these tons were disposed of in the waste stream. Thanks to the improvement in the end-of-life plastic management option and growing public awareness, the amount of plastic waste disposed in the landfill is constantly decreasing. Nevertheless, it's important to propose new alternatives to promote the recycling of these wastes. The main problem that's present in the polystyrene wastes are its low density, and this is responsible of a huge volume of wastes that should be transported, and consequently there are important costs associated. By this reason, it was thought to reduce its volume by means of compactation, but the problem is that during this thermal process there is an important generation of undesirable byproducts as a consequence of the thermal degradation of the polymer chains. To overcome this problem, we propose the use of suitable solvents that can achieve a volume reduction without degradation of the polymer chains. In order to get a feasible and economical process, we propose the production of a high added value final product as the microcellular foams. These microcellular foams presented very good properties, such as high impact strength, a high toughness, high fatigue life, a good thermal stability, and low dielectric constant and low thermal conductivity. In order to achieve this process, we propose the cycle that is shown in the slide. From polystyrene waste, we use terpene solvents that are agreed with green chemistry. They are essential oil from plants and fruits, non-toxic, non-flammable, environmentally friendly, and polystyrene present a high solubility on them. Once the solution has been performed, we propose the use of carbon dioxide to remove the solvent instead of the traditional vacuum or distillation. We decide to use carbon dioxide because it's inert, non-flammable, explosive, or toxic. It's very easy to obtain from the air. It presents a very low critical temperature and a moderate critical pressure. It's very easy to remove from the final product, can swell most of the polymers, and also it allows to tune the final structure of the microcellular plastic. Thus, when a solution of the solvent and the polystyrene is contacted with the carbon dioxide, the high solubility of the terpene oil and the total insolubility of the polymer will produce the phase separation, getting a polystyrene recycled and a side stream with the carbon dioxide and the solvent. Thus, the carbon dioxide, it will be used not only to induce the phase separation, but also to promote the foaming of the polymer and to get the microcellular foams. Thus, the general goal of this work is the production of polystyrene foams in supercritical carbon dioxide from polymer terpene oil solution. To get this general goal, we have drawn the next specific objective. Initially, we selected the working condition to carry out the foaming process. After that, the foams were characterized, and after the general process was optimized. The raw materials that were used were polystyrene. Also, we use real wastes that comes from Teknove, 2 natural solvents, cymene and limonene, and carbon dioxide as anti-solvent and foaming agent. Initially, we selected the working condition according to the glass transition temperature of the mixture that we measure in a high-pressure differential scanning calorimeter, and the interfacial tension that we measure by means of the pendant droplet method in a high-pressure view cell that was developed in Eurotechnica, Germany. After that, we carried out the foaming process in a homemade batch-type device where the solution is placed inside, and after the vessel is filled with CO2, the pressure and temperature were kept constant for 4 hours to assure a homogeneous nucleation, and after that, the system was vented by controlling a discharge valve. The characterization of the microcellular foam, our final product, were measured by means of scanning and optical electron microscopy, thermogravimetric analysis to determine the cymene or limonene amount, calorimetric analysis to determine the glass transition temperature of the final product, and also we determine the molecular weight distribution by means of chromatographic analysis. Finally, a statistical analysis was carried out to determine the influence of the studied variables on the response. The saturation of the foam should be carried out in a glassy or in a rubbery state, or at least near the TG zone. When carbon dioxide is sorbed inside a polymer, it produces a high mobility of the polymer chain and consequently a decrease of the glass transition temperature. By this reason, we decided to determine the influence of carbon dioxide on the glass transition temperature of the polystyrene. As we can observe in the graph, when carbon dioxide pressure increases, the TG decreases. But when we are close to 70 bar, the TG is kept constant, and this is because the saturation is finished. We decided to compare our data with other from the literature in order to check its reliability, and as we can observe in the presentation, they agree pretty well. Also, we decided to study the influence of a co-solvent, the limonene or the cymene, on the TG, and we observed that there isn't any important decrease in the TG of the ternary system because the presence of the carbon dioxide is mainly responsible of the decrease of the TG. To create a homogeneous microcellular foam, it's important to decrease the rate of homogeneous nucleation by means of a decrease on the Gibbs energy, and to get this, we can get it by lowering the interfacial tension. By this reason, we decided to measure, and we observed that independently of the pressure, the temperature, the solvent, and the concentration used, interfacial tension decreases linearly as the pressure of CO2 increases. So, as the foaming process should be carried out around TG zone and in a place where the interfacial tension should be the lowest, we decided to propose a design of experiment with these 3 variables, pressure, temperature, and concentration, at 2 different levels to study the influence on the microcellular foam structure. As we can observe, this is the design of experiment that we performed, and these are some of the most relevant microphotographs that we obtained. Independently of the solvent used, we can observe that at 70 bar and 40 Celsius degrees, any foam was obtained. This is because if we study the ternary system, the carbon dioxide mass fraction is the lowest, so probably it isn't enough to solubilize all the terpene oil and to achieve a dry foam. By this reason, we obtained just a solution. In order to optimize the process, we decided to study the cell diameter and its standard deviation to get a very low cells structure and very well homogeneous. According to the data obtained, we observed that when pressure increases, the CO2 absorption into the solution also increases. It causes a higher plasticization that is the responsible of the increase of nucleation because it able to lower the viscosity and create a higher number of nuclei that are able to nucleate. Nevertheless, when we increase temperature, we observe that higher cells were obtained and they weren't so well homogeneously distributed. This is because the carbon dioxide sorption decreases when temperature increases, and consequently fewer nuclei are formed. By this reason, the cells that are formed, they grow very, very quickly, but they grow on an asymmetrical way. Finally, we determine the effect of concentration on the diameter and its standard deviation, and we observe that although it isn't significantly influenced, we can see that at higher concentration, the carbon dioxide sorption into the polymer solution decreases. So there is a low nucleation rate that is responsible of the creation of bigger but more heterogeneous cells. According to these results, we perform the statistical analysis, and we can observe that the optimum condition to get the smallest and most homogeneous pore cells was obtained at 90 bar and 30 Celsius degrees. Finally, we determine the concentration of the remaining terpene oil that was inside the foams, and we observed that they were practically free of solvent, and also any change in the molecular weight distribution was observed. Finally, we compare the foams that we were obtained by means of this process with the extracted polystyrene, usually commercial, and we can observe that we were able to decrease the average pore around between 20 and 200 times, and that we were able to increase the cells density from 10 to 4, that is the commercial, to 10 to 9 or 10 to 11. So we can conclude that a proper forming of polystyrene at very mild working condition can be achieved by using supercritical carbon dioxide, and the structure of the microcellular foams that were produced can be tailored by varying the pressure and the temperature. So thank you very much for your attention, and if you have any questions.